Walk through the city of Yazd in central Iran on a July afternoon. The air outside is 47 degrees Celsius. That is 117 Fahrenheit. The sun has not let up for 9 hours. The streets shimmer. Every shadow is occupied. Every animal has stopped moving. Every tourist has retreated indoors. Now step inside one of the old houses in the historic quarter, a 600-year-old adobe home with thick mud brick walls and small windows. The temperature inside is 27 degrees Celsius, 80 Fahrenheit, a 20-degree drop. There is a steady, gentle breeze moving through the room. It smells faintly of damp earth. It feels almost humid in your throat. You can hear nothing. No fan, no compressor. You look up. There is a tall brick tower rising from the corner of the ceiling, square at the base, tapering at the top. That tower is 700 years old, and it is the only reason this house is livable. The Persians called it a bajir. The word translates literally as wind catcher. Yazd has roughly 700 of them. The tallest, at the Dawlatabad Garden, rises 33 meters above its courtyard, 8 stories tall. Built without nails, without electricity, without engineers as we understand the word. Just adobe brick, careful geometry, and a 4,000-year-old understanding of how air moves through a desert. UNESCO listed Yazd as a World Heritage Site in 2017. They called the city a living testimony to intelligent use of limited available resources for survival in the desert. What they were really describing is one of the most sophisticated passive cooling systems ever invented by human hands. A system that cools a 6,000 square foot adobe palace to comfortable temperatures. And in the United States, a country that spends $29 billion per year on residential air conditioning electricity, almost no one has ever built one. If you find these stories worth saving, the kind of engineering that came from people who had to survive without anything resembling modern infrastructure, subscribe to Cryptos. We pull these systems out of the archives, the field reports, and the buildings themselves. Every subscription helps these forgotten technologies stay alive online. Now let me show you how it works. The earliest references to wind catchers in Persian texts go back to the 5th century, but archaeologists discovered something stranger in 1969. Cooling structures dating back roughly 4,000 years. Some form of the bajir was being used during the Bronze Age, before paper, before money, before most of what we associate with civilization. The principle is that old. By the time of the Achaemenid Empire, around 500 BCE, wind catchers were a recognized architectural feature in Persian palaces and homes. Egyptian tomb paintings from a similar period show structures with the same function. Ancient Sindhi architecture in modern-day Pakistan used a similar design called mang. Across the Persian Gulf in Bahrain and the United Arab Emirates, traditional courtyard houses had wine towers integrated into their design for centuries. But the Iranian plateau is where the technology reached its highest expression. Yazd, Kashan, Kerman, Bam, Nain. Each of these cities developed slightly different versions of the bajir based on local wind patterns, dust conditions, and seasonal needs. The oldest surviving wind catcher in Yazd dates from the 14th century. That tower has been standing for 700 years. Adobe and mud plaster, vulnerable to rain, exposed to sun, sitting through earthquakes and political upheaval. And it still works. You can stand under it today and feel the breeze it pulls down from the sky exactly as the original builders intended. So how does it actually work? The bajir uses 3 different physical principles, sometimes simultaneously, to move air through a building. Each one is simple on its own. Combined, they are extraordinary. The first principle is wind capture. When wind blows across the top of any tall structure, the openings on the upwind side catch the moving air and force it downward. Pressure builds inside the tower. That high-pressure air then flows down the shaft and out into the rooms below. The size, height, and orientation of the tower determine how much air gets caught. In cities where wind blows reliably from one direction, like Maybad near Yazd, builders made wind catchers with a single opening pointing into the prevailing wind. In cities where wind direction changes seasonally, like Yazd itself, they built towers with 4 or 8 openings facing every direction. The tower captures whatever wind is available, regardless of where it comes from. The second principle is the stack effect. This is what happens when the wind stops. On still days, the wind catcher does not become useless. It reverses. The interior of the building, especially in stone and adobe homes with thick thermal mass, stays cooler than the air outside. Hot exterior air rises naturally. The dense, cool air inside the building flows toward the lowest pressure point, which is the bottom of the tower shaft. From there, it rises up through the tower because the tower itself, exposed to the sun, has heated the air column inside it. The hot air rises and exits through the top openings, creating continuous suction that pulls fresh air through the building from doorways, low windows, and any other ground-level opening. The building exhales upward through its own chimney. This is why a badger works even on completely calm days. The temperature differential alone is enough to drive airflow. The third principle is evaporative cooling, and this is where Persian engineering becomes genuinely brilliant. Many of the great badgirs in Yazd are not standalone towers. They are connected to two other systems. The first is the Qanat, an underground water tunnel system that brings cool water from mountain aquifers into the city. The second is the Abanbar, a deep underground water reservoir built specifically to store cool water year-round. When wind enters the top of a connected badgir, it does not flow directly into the living rooms. It first descends through the tower shaft into the basement, where it passes over the surface of the cool underground water. Some of that water evaporates into the moving air. Evaporation absorbs heat, significant amounts of heat, the same physics that makes you feel cold when you step out of a swimming pool. By the time the air emerges from the basement and rises into the living quarters, it has been cooled by evaporation by another 5 to 10 degrees Celsius. Combined with the simple shading and convection effects, the total cooling can drop incoming desert air by 15 to 20 degrees Celsius. That is the difference between 47 outside and 27 inside, the difference between unlivable and pleasant. The Boroujerdi house in Kashan, built in 1857, has two enormous wind catchers feeding the central courtyard. The Dolatabad Garden Badgir in Yazd is connected to a complex underground Qanat system that delivers water from mountain springs over kilometers of distance. The wealthy merchants and aristocrats of medieval Persia were not just building cool houses. They were building integrated environmental systems. The wind tower, the underground tunnel, the water reservoir, and the building itself were a single mechanical organism designed to keep human bodies alive in a climate that should kill them. Now let me walk you through how a badgir is actually constructed. This is not a technique you can copy in a weekend, but the principles behind it can be applied at smaller scales. You start with the chimney shaft. The tower is essentially a hollow vertical column. In traditional construction, the walls are built from adobe brick or fired brick laid in mud mortar. The shaft is square or rectangular in cross-section, typically between 0.5 meter and 2 meters across, depending on the size of the building it serves. The shaft height ranges from 3 meters above the roof for small homes to over 30 meters for palatial structures. Inside the shaft, traditional builders installed wooden crossbars at intervals. These crossbars served two purposes. Structurally, they helped resist the lateral forces that wind exerts on the tall, narrow tower. Functionally, they slowed the descending air slightly and helped distribute it more evenly into the rooms below. The key engineering detail is the internal partition. Vertical walls divide the column into separate channels. This is critical. Without partitions, air would simply blow back out the leeward side, creating a useless crossflow. The air entering one opening is forced to descend, while air rising from inside the building is forced up a separate channel. The same tower simultaneously brings cool air down and exhausts hot air up through different internal corridors. At the bottom of the tower, where it meets the living space, builders placed a small basin or pool of water. As descending air hit this water, evaporation cooled it further before it filled the room. In some sophisticated designs, dripping fountains or wet cloth screens were placed in the airflow path to enhance evaporative cooling. The walls of the tower itself were typically thick adobe, between 30 and 60 centimeters. This thermal mass kept the tower interior shaded and relatively cool throughout the hottest hours. Without that thermal mass, the tower would heat up and lose its ability to cool descending air. The exterior was finished with mud plaster, sometimes elaborately decorated. The badgirs of Yazd are status symbols, sculptures, and statements of architectural sophistication. Now here is where modern attempts at this technology often fail. The first failure is scale. Many homeowners try to build small wind catchers that are barely tall enough to clear the roof line. A badgir needs height to function. 1.5 meters above the roof line does almost nothing. 3 meters is the minimum. 5 meters or more is where the system actually starts to perform. The second failure is integration with thermal mass. A wind catcher feeding a balloon-framed wood house with vinyl siding will not produce the same cooling as a wind catcher feeding an adobe, stone, or rammed earth structure with thick walls. The cooling effect depends on the building itself acting as a thermal sink. Light frame construction sheds heat back into the interior almost as fast as the wind catcher delivers cool air. The cooling never builds up. The third failure is omitting the evaporation stage. A simple wind catcher delivers ambient air. If the ambient air is 47 degrees, you get 47-degree air. Dramatic drops require passing that air over water. The fourth failure is climate mismatch. Wind catchers work best in dry, hot climates. They struggle in humid climates because evaporation does not cool air that is already saturated with moisture. So why has this not been adopted in the American Southwest, where climate conditions match Yazd almost perfectly? The answer is partly cultural and partly economic. American building codes are written around mechanical heating and cooling systems, certified by manufacturers and installed by licensed HVAC contractors. The International Residential Code provides no prescriptive pathway for a passive wind tower as a primary cooling system. A homeowner who tries to build one needs to use the Alternative Materials and Methods Clause, which requires custom engineering review, special inspections, and approval from a building official who has never seen the technology. Banks do not recognize passive cooling systems as adding value to a property. Real estate appraisers have no comparable sales to reference. Insurance companies treat unconventional architecture as elevated risk. HVAC contractors have no incentive to recommend a system that competes with the equipment they sell. And the air conditioning industry in the United States, currently worth roughly $17 billion annually for residential equipment alone, has built every aspect of its business model around mechanical cooling that consumes electricity and requires periodic replacement. The Persian wind catcher does none of those things. It is built once. It costs nothing to operate. It needs no electricity, no refrigerant, no maintenance contract. It outlasts the family that builds it. It is, in every commercial sense, hostile to the modern HVAC industry. Meanwhile, climate-conscious architects in Australia, France, and the United Arab Emirates have begun integrating Badger-style towers into modern buildings. The Council House 2 in Melbourne uses 3-story shower towers based directly on the Persian principle. The Saint-Étienne Zenith in France uses a similar concept. The Masdar City project in Abu Dhabi has revived the wind tower as core architectural infrastructure for an entire planned city. Every one of these projects exists because architects studied what the Persians figured out 4,000 years ago and decided to copy it. In the United States, the same technology is not banned. It is not illegal. It is simply absent from the conversation. No code recognizes it. No tax credit subsidizes it. No bank finances it. No insurance company underwrites it. The result is that an engineering tradition perfected over millennia in climates almost identical to Phoenix, Tucson, Las Vegas, and El Paso has been quietly excluded from the American architectural toolkit. And here is the practical bottom line. You cannot easily build a Yazd-style wind catcher on a conventional American suburban home. The integration with thermal mass, water reservoirs, and qanats is not realistic in most American settings, but the principles are scalable. A small chimney tower added to an earth-bermed addition, a solar chimney exhaust vent on a workshop or greenhouse, a passive ventilation tower on an outbuilding. These are projects within the reach of any homeowner with land, time, and the willingness to learn. If you want to start, do not build a Badger on your house tomorrow. Visit Yazd if you ever can. Read the work of architect Susan Rofe, who documented these structures in detail in the 1980s. Build a model first. See how the geometry works at small scale. Then think about which building on your property might actually benefit from passive ventilation that costs nothing to operate after the day it is finished. The wind is still blowing across the Iranian plateau. The towers are still standing. The physics is the same in the American Southwest as it is in Yazd. The only thing missing is the willingness to build something the air conditioning industry has spent 50 years convincing us we did not need.